we're going to talk about more linear models. Although here we're going to talk about just general linear models. Before we talked about specifically ones with money, with the cost, revenue, profit, all that good stuff. Now we're going to talk about models in general. So first thing is let's define it. Maybe we'll find it. Mathematical model is a function that represents a real world scenario. Pretty simple. So we create a function that's going to help us predict something that's going to happen in the real world, depending on certain input and other information. So the first one. Population of rhinos in 2000 was 3,800. It had grown to 4,400 by 2012. First, find the model representing population rhinos T years after 2000. Then we want to estimate the population in 2021. And then when do we predict population will reach 5,300 rhinos? So the first thing, and very important, is that we're going to assume a linear model. Not all models will be linear, represented by a straight line. But for this one, we are going to assume that. Later on, we'll get into some exponential models in other situations with logistical, logarithmic, polynomial. So we'll see all kinds of different ways we can do this. So the first thing is we have to identify our variables. T will be time, and we can use P for our population. Now that we know what our variables are, we need to figure out which one is going to be the independent that we control and which one is the dependent that we then try to predict. So time, even though we don't really control it, we are going to be able to pick it. So that's going to be our independent. And that would make our population the dependent. Since we are dealing with linear models, we need to come up with the information we need for a linear model. So we're going to write this in our slope intercept form. So it's a y equals mx plus b. We need our slope, and then we need our y-intercept. So let's find our slope. It's a rise over run. Rise is the y values typically, which is the dependent. So it's our population. So we'll do 4,400 minus 3,800. Our independent variable is time, but they mentioned something here is that T years after 2000. So we need to make an adjustment. So 2000 is going to be 0, and 2012 will just be 12. And make that 0 look like the 0. A little bit better. So now it's 12 minus 0. Now, if we would use 2012 and 2000 in this situation, it would not make a difference now. when we're finding our slope, because the difference is still the same. But later on, when we plug in our t's, that will make a difference. So it is 600 over 12. So that gives us 50. So we need to come up with our equation. And I need to move things out of the way. There we go. So our population, it doesn't really matter which one we pick, although I would strongly recommend picking the 2000, because we're going to see in a second, it's going to be really easy and it's a nice number when we can use a 0. So 3,800 is going to equal 50 times 0 plus our b value. So therefore our b is just going to be our 3,800. So our population, which is a function of time, is going to be 50 times t plus 3,800. So there's our answer for A. For B, I like that. For B, and we'll clear the page, we want what is a population in the year 2021. So let's use our, if we went 2021, that's 21 years after the year 2000. So our t equals 21. So therefore P of 21 is 50 times 21 plus 3,800. 50 times 21 is 1,050. Plus our 3,800. Therefore, 4,850 rhinos in the year 2021. The last question asked, when will we reach 5,300? So that's our new population. We're looking for a t. Subtract your 3,800 over, and that's going to be 1,500. Divide by a 50. And now a nice thing about division is we can do this fairly easily, that our zeros are both going to cancel. So 150 divided by 5, 15 divided by 5 is 3, then a 0. So it's going to be 30 years. If that actually looks like it in RS. So in the year 2030 is when we're going to reach the population of 5,300 rhinos. Let's do another one. The population of West Virginia was 1.826 million in the year 2010. By 2017, it was 1.817 million. Make sure I spelled that correctly because I can't see. Okay. Too many things on the screen covering things up. So we want to A, find the model. And we want to round to 6 decimal places. And B, when will the population, well, actually, when do we expect population to fall below 1,798,000? So now we have some choices. The information does not tell us anything about where we want our starting year. So if you want, we could do what we did before and take our T to be years since 2000, just to make smaller numbers. So that would be 10, and that would be 17. Now, the key here is whenever we do our work, we have to understand and remember that T is years since 2000. So if your answer is 30, we're not going to do things in the year 30, it's got to be added on. So something to keep in mind. So again, we need our independent variable and our dependent variable. Just like before, population will be dependent. And we also have a choice of how we want to write this, that we're going to make our answer give our results in millions. So if the answer comes out as a 3, that means 3 million. And then 17 minus 10. So notice that this is a negative result that we get here. And just to make this a little bit nicer so I can spread my numbers out, we can actually read them. There we go. So negative 0.001286, and that is millions of people per year. Because we had millions of people on top, years on the bottom. So our population is going to be a negative 0.001286t plus some b value. And let me make that a little bit nicer here. So it doesn't matter which one we use. Let's use smaller numbers. And since we have a nice 10, multiplying, we get a negative 0.01286. Easy multiplication. All we have to do is move the decimal over 1. Add that to the other side. We're at 1.83886. So our final equation is P of T equals our negative, and I'm going to delete this real quick, just because it'll be neater and a bit faster. Our final equation, if I type it, (83886). Okay. So thinking about what all this means, since our T was years since 2000, in the year 2000, there were 1.83886 million residents of West Virginia. Now let's use that equation. And we want to figure out when our population is 1,798,000. But we have to write it in the correct way. So it's 1.798. And now subtract our 1.83886 over. And it's going to be a negative. And that is 0.4086. And we still have this on the other side. So we're going to do some division. And we end up with and actually, let me double check this. Okay, yep, we're good. And then divide that by negative 0.001286. And we end up with T equals 31.77. That should be a 7. 2,939,3468 years. But we want to know when this is going to happen. So 31 years after, so roughly around the year 2031. And 0.77 into the year. So 3/4 of the way in, sometime around September is when we would expect that. All right, next one. Anyone who has ever traveled internationally knows the importance of the conversion between Fahrenheit and Celsius. So, traveling to other countries that use metric, whenever they tell you that the temperature is going to be 30 degrees out, definitely don't wear your parka, because 30 degrees in Celsius is pretty warm in Fahrenheit. It's around 80. So what we're going to use, and it really does not matter which one we use as an independent or dependent. Well, it depends on which way we're going from which one to which, but we can always make adjustments. But let's have our freezing point, which is going to be 32 degrees Fahrenheit and 0 degrees Celsius. And then the boiling point of water is 210 Fahrenheit and 100 Celsius. So we're going to use those two numbers. And it's not going to make much difference how we set it up. We can actually do both if you'd like. But let's do our Celsius on top. And let's make that a little bit nicer. Doesn't run together. Celsius also almost made his scale backwards. He was actually thinking of having boiling point at 0 and freezing point at 100. The things you learn on Jeopardy. So if we reduce this, and it's real nice and easy that we can cut out the zeros, and then 10 divided by 18 is the same as 5/9. And so this is going to be degrees Celsius divided by our Fahrenheit. So Celsius has to be our dependent, variable 5/9 F plus 32. Whoops, sorry, not plus 32, that's plus our B. So we have to find what is that B. So let's pick one of them, and using zeros just as easy. And then doing our multiplication. That's going to be 160/9. So negative 160/9 equals B. So our equation, if we have our Fahrenheit, and we're going to change to Celsius, is right there. Now, what if we go the other way? So we're going to take this exact same equation, and first I'll highlight this. And now let's solve for Fahrenheit. So we can add that 160/9 over to the other side. And now we can do one of two things. We are multiplying by 5/9, so we can either divide by 5/9 or multiply by the reciprocal, multiply everything by 9/5. Now, whenever we distribute this, you get 9/5 times C plus, and then the nines will cancel, and we're left, instead of multiplying the whole thing out, the nines will cancel, and then we have 160 divided by 5, which is a little bit of a nicer equation. That's more recognizable because we have that plus 32 in there. Well, let's use this top one, and let's see what happens whenever we want to find or convert 70 degrees Fahrenheit to Celsius. So we're looking for C of 70 for making it in our function notation. So that is 5/9 times 70 minus 160/9. 5 times 7 is 35. Add the 0. And look, we have common denominators, so we can combine those together. Subtracting, that gives us 190. And then if we do our division there, it's going to be 21.1 degrees Celsius. Now let's convert 70 degrees Celsius to Fahrenheit. So we could use the other equation, but let's use this one, that's 70 5/9 F minus 160/9. We can add the 160 to the other side, but 70 plus 160 divided by 9. We need common denominator, so we'll multiply that by 9/9. 9 times 7 is 63. So 630 plus 160/9 equals our 5/9 F. That would give us a 790. And just like we did before, we can multiply both sides by 9/5, and they'll both cancel. Multiply this side by 9/5, And those will both cancel. And so doing our division, 5 goes into 7 once, 2 left over. 5 goes into 29 5 times, 4 left over. And 158 degrees Fahrenheit. I think I like 70 degrees Celsius better, or 70 degrees Fahrenheit better than 70 degrees Celsius. And now if we would have used that other equation that we had, that F of 70 is equal to 9/5, 70 plus 32. We can either do our multiplication or division first. This is really 70/1, and we can simplify this and make that a 1 and a 14. So just canceling or reducing our fraction. 14 times 9, so 10 times 9 is 90. 9 times 4 is 32, so 36, so 6 plus 32, which gives us 158. A little more straightforward, but we already did all the work to do our conversion. Let's do another one. So let's bring back some of the business problems. Just get some extra practice with those. A company has a marginal cost of $30 per item. It can produce 5,000 items for a total cost of $200,000. Find the cost equation. All right, so important words here. First, whoops. All right, now that we have that. Oh, there we go. Let's redo. There we go. Now it's back. Change our font. Marginal cost. Marginal cost, that is your slope. So our cost equation is going to be 30x plus something. And then let's use the information they gave us. Cost of $200,000 is going to be from 5,000 items. And now 5 times 3 is 15. And there are 1, 2, 3, 4 zeros. Subtract over, we get 50,000. So our equation for cost, here I'll type this out to make it a little bit nicer, is going to be our 30x, because that was our marginal cost, plus our $50,000 for the fixed costs. Next. Company has a fixed cost, or has fixed costs of $5,000, and they make $12,000 in profit from the production of 200 items. Find the cost, or excuse me, the profit equation. So profit is gonna be the marginal profit times X minus fixed costs. We know what our fixed cost is. They gave that to us. We know a certain profit and a certain number of items. So 12,000 is the marginal profit, and we'll put that in parentheses, times 200 minus 5,000. So let's add 5,000 to both sides to get rid of it. And that's 200 times the marginal profit. Let's do our division. So 17,000 divided by 200. That's our marginal profit. Cancel out some zeros. So that's going to be 85. So they make $85 every time they sell an item. So they have an $85 markup. Not bad if you can get away with it. But our equation for profit will now be 85x minus 5,000. So we went through some of our different models for just general case with linear predictions. And that's it for today.